Welcome back. This is the last module of the course. So far we have discussed CTMCs, continuous time Markov chains. Today we will discuss semi-Markov processes, which are like a generalization of CTMCs, as well as, in fact, there are also generalization of renewal processes. All right. So a semi-Markov process is characterized by two things. So you are given DTMC, let's say a countable state DTMC, embedded DTMC. Okay. So Xn is a countable state embedded DTMC, just like for CTMCs, and then you have holding times which are not necessarily exponential. All right. For a Markov process, you have in each state you have a exponential holding time. So if you are in state j, you hold for exponential nu j, right. In a semi Markov process, you can hold for any general distribution. Okay. And the way it works is that so you are given, let us say, given xn minus 1 equals j, or maybe it is xn minus 1 equals I and xn equals j. Okay. So this happens with probability Pij, right. So this transition probability Pij is given. The holding time in the holding time is distributed according to some CDF Gij. Okay. So to draw, maybe I should draw a picture. So you have, let us say that's time 0, and so you have, this is S1 where the first transition occurs, this is S2 dot dot dot, this is Sn minus 1, Sn and these we will denote by U1, just like in CTMCs and so on. So this will be UN, all right. And of course the state transitions here will be, so the states of the DTMC, right, embedded DTMC state, x naught, x1, xn minus 1, xn. Okay. So SNs are the epochs. Okay. Sn is the epoch where the transition, the nth transition takes place, and xn is the state of the embedded DTMC at the nth transition. Okay. So you can say that, so let us say if xn is in some state I, xn minus 1 is in state I and xn equals state j, then probability of un less than or equal to u, given xn minus 1 equals I, xn equals j, is just some g I j of u. Okay, this is some CDF. Okay. So notice that we are allowing the holding time to not just depend on which state you are in, it could also depend on which state you are going to, all right. Of course, the case where the holding time does not depend on j is a special case of this, and in fact in the CTMC case the holding time depended only on the state that you are in, not which state you are going to, right. But in a semi Markov process we can even allow that, there is no law, I mean there is no problem in allowing this. Okay. Now the dependence structure, I should tell you a little bit about these dependencies, right. What we are going to say is that this un random variable, so let me write this down, the dependence structure. So this is for u greater than or equal to 0, and un is independent of um for m less than n and independent of xm for m less than n minus 1. Okay. So, the dependent structure is like this. So, you have x naught, okay, and then x 1, okay, and these two, x naught is the first state of the embedded DTMC, x 1 is the second state. These two together can determine u 1 and x 2. So, uh, so x naught, x 1, x 2 etcetera evolves according to a DTMC, right, that we already know, right. So, condition on x 1, x naught and x 2 are independent, all that we already know. Now, the dependence of u's are such that now u 2 dependence is only between x 1 and x 2, all right. So, u 2 is independent of u 1, okay, and u 2 is also independent of x naught, and generally u n is independent of x n minus 2 and so on, okay. So, this is the dependent structure dot dot dot, okay. So, we will denote the mean of the Gij distribution using u bar I j, all right. So, in particular I e u bar I j is just integral u greater than or equal to 0 1 minus g I j of u. So, I am just integrating the complementary CDF, right. I can integrate the complementary CDF to get the mean, that is because this is a non-negative random variable, okay. So, this is just a notation, u bar I j is the mean holding time in state I if you are going to state j next, okay, and let u bar j or u bar, let us say u bar I as expected u n given x n minus 1 equals I. This is the holding time in state I, now unconditioning on what the next state is, okay. This will simply be sum over p I k u bar I k, okay, sum over all these states. So, I am just taking, so u bar I k is the expected holding time in I given that you are going to k, right. Now, I am averaging over all the p I k's, this is just the total expectations, right. So, this is the average holding time in state I, unconditional of where you are going. So, these two are useful notations, okay. Now, everything that we really need to know about these semi Markov processes follows similarly in terms of time average and all that, follows similarly to the CTMC case, okay. So, if you want to look at the average fraction of time spent in some state j, in the CTMC case we got, you know, if pi k was the underlying distribution of the embedded Markov chain, we could get Pj as, you know, pi j over nu j divided by sum over pi k over nu k, right, assuming that the denominator is finite. Actually, even if the denominator is infinite, it is still correct, except you have Pij is 0 in that case. Similar, something very similar holds here, the arguments are almost identical, okay. The point is that if you look at you know, Mij of t as you did in the CTMC case, say if you look at this counting process, be the number of transitions into j given x not equal to I in the interval 0 t given x not equal to I, all right, and mi of t equal to total number of state transitions, total number of state transitions by the embedded DTMC in 0 t. Okay, these are exactly the same notations we used as for the CTMC case. What we can show is that Mij of t is a delayed renewal process. So, you are going from I to j first and then you are going from j to j again and again. So, successive entries into state j will be IID, okay, independent and identically distributed. That is because of the strong Markov property of the embedded Markov chain and the fact that the u random variables have a certain independence property as well. Okay, using these two facts, I mean this requires a proof, right. I mean I am not getting into the proof of this in great detail, but you can show this. First of all, you have to show that you know these successive transitions happen in finite time with probability 1 and all that requires a proof. But they are, I mean they are essentially similar to what we did for CTMCs. So, you can show that Mij of t is a delayed renewal process, right, using the definition of the semi Markov process. So, you can use the same machinery to show a theorem like this, which is analogous to what we did for time average occupancy of states in the CTMC. Excuse me. Consider a semi Markov process with an irreducible and positive recurrent embedded DTMC and let pi j be the steady state probabilities of the embedded DTMC. Okay, so you are taking a nice embedded Markov chain which is irreducible and positive recurrent and it has pi j as its steady state probabilities, and you are taking let us say some let x naught be the starting state, x naught equal to I be the starting state, then number 1, the limiting fraction of time spent in any state j is given by Pj equal to pi j u bar j over sum over k pi k u bar k, okay, with probability 1. This is a fraction of time spent in state j with this is almost surely equal to pi j u bar j over sum over pi k u bar k. Okay. This is a valid probability distribution if the denominator is finite. If the denominator is infinite, you will get 0. Okay, there is no meaningful notion of fraction of time spent in any state. All right. So, if you think about this u bar j is playing the generalized role of 1 over nu j in the CTMC case. So, in the CTMC case, you got pi j over nu j divided by sum over pi k over nu k, right. So, 1 over nu j is simply u bar j. Remember that u bar j was defined here, right, is the average, it is the average holding time in state I, irrespective of where you are going. So, u bar I j does not directly matter, right, although we allow this u n to depend on I as well as the next state j, u bar I j does not directly matter. What really matters for this average fraction of time is this u bar j, u bar I, all right. So, this is all from renewal, this is along the same lines as the proof for CTMCs. Okay. If you think about it, in the CTMC case, we had a reward of 1 for whenever you are in state I. So, we consider the delayed renewal process mij of t, and whenever you are in state whatever state j, right, you are interested in, you give a reward of 1, right, and it turned out that the average reward in that state was 1 over nu j. Now, that 1 over nu j will simply be u bar j, that is all, okay, and everything else follows identically. We can also we can also derive the expected renewal interval of successive returns to state j, which is w bar j. This is the expected time between returns to state j, which is equal to sum over pi k u bar k over pi j, all right. So, remember that pi j w bar j was constant in the CTMC case, it turned out to be some constant, right, and which we could find out later, and something similar holds even in the semi Markov case. Okay. And finally, we can write out the rate of transitions. Transitions take place is independent of x naught. It does not matter which state you start in, and is given by, what is the average rate of transition? It is simply limit t tending to infinity mi of t over t, which is just 1 over sum over k pi k u bar k. So, remember in the CTMC case, you got pi k 1 over sum over k pi k over nu k, right. Here you are getting instead of 1 over nu k u bar k. Okay. This is also almost surely, or with probability 1, whichever you like. Excuse me. All right. So, these are analogous, it follows almost identically to the CTMC proof for the corresponding quantities. So, I will not bother getting into the proofs again. Okay. So, we have the average fraction of time spent in state j, average rate of transitions, average time between transitions to state j, and all that worked out, all right. There is one more thing that is of interest in semi Markov process, which was not very important in the CTMC case. It is the average fraction of time that maybe I should also state this as a part of the theorem, which also comes from renewal reward. We should, the fraction of time, let me just state it first, time t over which x t equals I, and the next transition goes to j is given by let us say qij, let us call that qij, it is given by pij of the DTMC u bar ij over w bar of I, which if you rearrange becomes we know the expression for w bar I from that, right. If you just put that back in, so you want to write, we do not know what w bar is, it is not specified as such in the process, right. So, we need to use this expression to get it in terms of the u bars, right. So, you will get Pij Pij u bar ij over u bar I. Okay. So, the fraction of time t, so if you look at, let us say you are in state I here, you could go to some other state, right. So, you know the fraction of time you are in state I is already known, right, which is pi, but you want to look at the fraction of time for which you are in I and the next transition goes to j. Okay. So, you give a reward of 1, let us say, let us call this Rij of t or some such, right. Let us call this, you consider the renewal process Mj of t and you look at sorry, so you look at the renewal process, let us say Mi of t, let us say this is a renewal process and you give a reward of Rt equals 1 whenever you are in state I and the next transition is to state j. Okay. But if you are in state I and the next transition is to state k, you do not give any reward, okay, you get 0 reward. You would consider this reward process, you can consider, you can easily calculate the fraction of time that you know you spend in state, the fraction of time you spend in state I transitioning into state j, okay, that is comes out like this. So, this is clearly, I mean, this is the w bar I in the denominator is the is x bar, right, for this renewal process, and Pij is the probability with which that u bar ij is the average holding time, right, whenever you are in state I transitioning into j, but you also have a Pij factor because you could go into any one of the other states as well, right. Pij is the probability with which you go from I to j. In that case, you collect a reward of u bar ij, right, that is the duration in which you stay, right. This is typically u bar ij duration, right, the expected duration is u bar ij. From this you can calculate this quantity, alright, good. So, these things you can calculate using renewal processes.